Okay, guys, topic 1.4 is going to talk about carbohydrates and also lipids in your notes. So, as we talk about a carbohydrate, I want you to think about your notes for both of these. We're going to talk about the monomers for carbs, and then we'll talk about the polymers. What happens when you link the monomers together? Specific examples, and then we'll address the function. We'll do the exact same order for lipids, and the reason we look at structure first, right? So we're going to look at the monomer and the polymer first, is because structure determines function. So we look at the structure of a monomer. We see right here in this diagram a whole lot of carbons, hydrogens, and oxygens. Notice there are no sulfurs, there are no phosphates, there are no nitrogens. It's just carbons, hydrogens, and oxygens. And they are in a particular ratio, a 1 to 2 to 1 ratio. So for example, glucose, C6H12O6, your carbon and oxygen count is the same and your hydrogen count is doubled. Now that might flux a little bit as we start to build polymers because remember we lose water each time we form a bond, but the monomer will always follow a 1 to 2 to 1 ratio. If you notice, there are a lot of hydroxyls or OH groups on this monomer. So here's one right here, 2, 3, 4, 5. Hydroxyls make substances soluble in water. And so a simple carbohydrate or a simple sugar is going to dissolve in water because of those hydroxyls. Now we do have a general name for the monomer of a carbohydrate. It's called a monosaccharide. Saccharide means sugar, and you can see the mono in front indicating one simple little sugar subunit. There are actual specific names to monosaccharides, but the terms that we have seen so far, the term of a monomer is a generic term for any monomer of a carbohydrate. There's actually two primary types of the monosaccharide. There's an alpha and a beta form, and we are going to read an article and talk more about alpha and beta linkage in class this week. Carbohydrates also end in the name OSE. So think about glucose and fructose and lactose. You'll notice that these words end in OSE. Carbs typically end in OS. I wanted you to see over here, a lot of times we see carbs in a ring structure. So this is a monosaccharide in a ring structure. But this is still a carbohydrate. All three of these are carbohydrates. So think back to our basic properties. Carbon, hydrogen, and oxygen only in a 1 to 2 to 1 ratio. These just happen to be linear. And so as you look at molecules, sometimes you will see linear molecules and you'll be tempted to label them as the other macromolecule that we're getting ready to talk about, lipids. Look at hydroxyls. If there are hydroxyls on the monomer, it's a carbohydrate. Carbs can exist in a linear form. There is one strange sort of difference here in the carbohydrate world. There is an intermediate molecule that is called a disaccharide. And so what I mean by that is most of the times we go straight from a monosaccharide, we go straight from talking about a monomer to talking about a polymer. But in the carbohydrate world, there's actually a special name for just a 2 subunit carb. And that is called a di. Di as a prefix means 2. Saccharide, there's that sugar component. So this is just 2 monomers linked together. And so you can see this was one monomer. The pink ring was glucose, and the orange-ish ring was fructose. they bond together and create a new specifically disaccharide sugar called sucrose, which is table sugar. Now, there are some other disaccharide examples right here that you maybe have heard of. Sucrose, we just said, is table sugar. There's lactose, which is the sugar that's in milk, and also maltose. Notice, ending of the words, OSE tells us it's in the carbohydrate world. So a true monomer is called a monosaccharide. If we link just two of those monosaccharides together, we will get this intermediate form of a disaccharide. If we attach a third one or go beyond, then we're finally into the world of a polysaccharide. So a polymer that is generically called a polysaccharide. Here are the four primary polysaccharides, the four that we specifically will be talking about. And so when you look at the structure, you can still see the individual little monomers linked together. You can see them here. There's a monomer, there's a monomer, there's a monomer. So you can still find the monomers here linked together. Anytime, again, three or more, we're going to call it a polymer. These are covalent bonds between the individual monomers, and the name of the bond is called a glycosidic linkage in a carbohydrate. So don't get confused. The process of forming the bond is dehydration synthesis that we've already talked about. But the bond that is formed is a specific type of covalent bond called a glycosidic linkage. Four primary types of carb polymers: starch, glycogen, cellulose, and chitin. So we will come back to these in just a moment as we talk about the function. And I want you to notice these two, they're kind of bubbly in formation, almost a little bit looking like the coiled up spring. And then these two are very linear in formation. And so we know structure determines function. And so we will see that some of these share a particular function while others share a completely different function. So as we step into the function world, those two primary functions of carbohydrates are energy. And the energy molecules are really made up of a bunch of alpha. I dropped just a second ago that there are two different types of monomers. There are alpha and then there are betas. And so we're going to spend time talking about that this week. But the energy molecules are made of alpha monomers. These are starch and glycogen. So these first two right here that are very sort of look like a spiral pattern, they serve as energy molecules. So the difference between them is where they exist. This starch is energy stored in a plant, and glycogen is energy stored in an animal. The other function of a carbohydrate is as a structural molecule, and these are when the beta monomers get together. And so cellulose and chitin, you can see how linear and almost rigid they are. They're going to provide great structures. So cellulose is found in a plant cell wall, providing structure to that plant cell. Chitin, okay, so not chitin, chitin, like a kite that you would fly. Chitin is the structural carbohydrate in a fungal cell wall, so a fungus cell. And it is the exoskeleton of an insect as well as crustaceans like lobsters and crab and shrimp. And so again, because the structure of something determines its function, there has to be something unique about these alpha and these beta monomers, and we will explore that uniqueness this week. That uniqueness is what allows for monomers to link up in sort of a spiraling pattern and provide energy versus a very linear pattern and provide a structural element to a cell wall or an organism. Now, our next macromolecule that we're going to talk about is a lipid. And so lipids are a pretty big and broad category. And so we're going to actually start with a bit of a lipid video. So all you have to do is watch as I play this.
Olive oil is 100% fat. There's nothing else in it. Pancake mix, on the other hand, is only about 11% fat. And yet olive oil is good for you, and pancake mix is not. Why is that? As it turns out, the amount of fat we eat doesn't impact our weight or our cholesterol or our risk of heart disease nearly as much as what kind of fat we eat. But let's back up. What is fat? If we were to zoom in on a salmon, which is a fatty fish, past the organs, past the tissues, into the cells, we would see that the stuff we call fat is actually made up of molecules called triglycerides, and they are not all alike. Here's one example. Those 3 carbons on the left, that's glycerol. Now you can think of that as the backbone that holds the rest of the molecule together. The 3 long chains on the right are called fatty acids, and it's subtle differences in the structures of these chains that determine whether a fat is, let's say, solid or liquid, whether or not it goes rancid quickly, and most importantly, how good or how bad it is for you. Let's take a look at some of these differences. One is length. Fatty acids can be short or long. Another, more important difference is the type of bond between the carbon atoms. Some fatty acids have only single bonds. Others have both single and double bonds. Fatty acids with only single bonds are called saturated, and those with one or more double bonds are called unsaturated. Now, most unsaturated fats are good for you, while saturated fats are bad for you in excess. For saturated fats, the story pretty much ends there, but not for unsaturated fats. The double bonds in these molecules have kind of a weird property. They're rigid. So that means that there are 2 ways to arrange every double bond. The first is like this, where both hydrogens are on the same side and both carbons are on the same side. The second way is like this. Now the hydrogens and carbons are on opposite sides of the double bond. Now, even though both of these molecules are made up of exactly the same building blocks, they are 2 completely different substances, and they behave completely differently inside of us. The configuration on the left is called cis, which you've probably never heard of. The one on the right is called trans, and you probably have heard of trans fats before. They don't go rancid, they're more stable during deep frying, and they can change the texture of foods in ways that other fats just can't. They're also terrible for your health, by far worse than saturated fat, even though technically they're a type of unsaturated fat. Now, I know that seems crazy, but your body doesn't care what a molecule looks like on paper. All that matters is the 3D shape, where the molecule fits, where it doesn't, and what pathways it interferes with. So how do you know if a food has trans fat in it? Well, the only sure way to know is if you see the words partially hydrogenated in the ingredients list. Don't let nutrition labels or advertising fool you. The FDA allows manufacturers to claim that their products contain, quote, 0 grams of trans fat, even if they actually have up to half a gram per serving. But there are no hard and fast rules about how small a serving can be, and that means you'll have to rely on seeing those key words, partially hydrogenated, because that's how trans fats are made, by partially hydrogenating unsaturated fats. So let's go back to our olive oil and pancake mix from before. Olive oil is 100% fat. The pancake mix is only 11% fat. But olive oil is mostly unsaturated fat, and it has no trans fat at all. On the other hand, more than half the fat in pancake mix is either saturated or trans fat. And so even though olive oil has 10 times as much fat as pancake mix, it's healthy for you, whereas pancake mix is not. Now, I'm not trying to pick on pancake mix. There are lots of foods with this type of fat profile. The point is this. It's not how much fat you eat, it's what kind of fat. And what makes a particular fat healthy or unhealthy is its shape.
Okay, so a lot going on here in the fat or lipid world. So let's first start with the monomer for a lipid. Well, here's the deal. There really isn't one. There are so many different kinds of fats, and they take on so many different shapes that there is no true single building block or monomer. However, there are usually at least these 2 components within any fat. There's going to be something called a glycerol head that attaches to fatty acid tails. And so these tails are loaded with carbons and hydrogens. They become giant long hydrocarbon tails and provide the majority of the molecular properties. They come from these hydrocarbons. And so in this picture up here, you can find the glycerol. So here's the glycerol that attaches in the 3 fatty acid tails. Here is another glycerol molecule attaching in 2 long fatty acid tails, and then a few things above it as well. Both of these are fats that we will end up needing to know, and so we'll see them again in just a moment. Now remember that lipids, because of those hydrocarbon tails, are going to be primarily nonpolar and hydrophobic. There could be a few lipids that have polar regions on them, like this one right here, and we'll talk about that in just a second. Now, when it comes to the tails, there's actually a couple of tail types. And the first video alluded to it, and so I might save this video for our classroom time to just kind of review it as a topic. But the tail types we're getting ready to see on the next slide. They are saturated tails, and then they are unsaturated tails. So let's look at the difference between these two. So this picture exists in your notes. And so just looking at both of these, I see some similarities. I see up here is our glycerol head, and then I see here is our hydrocarbon tail in both. So they both have the same sort of basic components, but they do not look the same. This one is very straight and linear. This one takes a bit of a bend. And so if you notice this region of the molecule, that becomes very important and is the basis for what is a saturated and an unsaturated fatty acid structure, which then of course determines some properties about these different tails. So for the saturated tails, there are single bonds only throughout the hydrocarbon tail. So all single bonds between these carbon and then single bonds out to hydrogen. Because there are single bonds only, the tail remains straight. The trick with saturated fatty acid tails is that because the tails remain straight, they actually can stack up one on top of the next on top of the next fairly easily. And so then we start talking about, if we're stacking fats, we can build up these things called plaques in our arteries. Clogged arteries might be something that you have heard of before in just kind of regular terminology. These fats are typically unhealthy fats, and they cause heart disease. A lot of fat stored in animals is saturated fat. And so a lot of the saturated fat that we consume comes from animal meat and animal product. The unsaturated tails, you'll notice there is at least one, sometimes many, double bonds. And the double bond actually bends the tail. And so now the tail isn't straight, which means it cannot stack up on another straight tail. And so what we see is that these unsaturated tails actually do not clog arteries. They remain liquid. They're liquid at room temperature. They're liquid as they flow through our arteries. And so they are considered our healthy fats. Think of olive oil, avocado oil, coconut oil, and you will think of healthy unsaturated fats. Now there is a third type of tail, and it's right here in the middle of this diagram. It's right down here at the bottom of this diagram. This is called a trans fat, a trans fatty acid tail. And so you might have heard of a trans fat before. If you have, perhaps bells go off in your head. These are bad, 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 bad for us. Our video referenced trans fats. So essentially, what you've done is scientifically, through a process that requires a lot of heat and pressure, you have taken an unsaturated fat with double bonds that should have a kinked tail, and you have straightened it out to mirror something closer to a saturated fat. So down here we have characteristics of both, an unsaturated and a saturated at the same time. Unsaturated because they're double bonds, saturated now because it is compressed and has straightened. So all of those straight tail properties about clogging up your arteries will apply to this. But the trick is that our body has a hard time digesting these because they're not natural. They're only created through a man-made process called hydrogenation. And so not only do they clog up our arteries, but also it's hard for our body to really make good use of them. And so they're clogging and stacking and occluding at pretty significant rates because we can't metabolize them very well. So why in the world would somebody even invent these? Well, two reasons really. They increase the shelf life of a lot of products, and they're really, really tasty. So they light up the pleasure and taste centers of our brain, and they can become addictive, actually. So two natural tail types, saturated and unsaturated, and then one man-made tail type that is really not good from a health perspective. Let's talk polymers. So you have 4 different pictures in your notes. These are the 4 polymers. Just like we saw 4 polymers for carbs, we're going to see 4 primary polymers for lipids. So you need to make sure that you can understand on the diagram. A lot of these are labeled, but you might want to relabel them and then also write down a couple of characteristics. So this first one right here is a triglyceride fat. Tri means 3. So this is a 1, 2, 3-tailed fat. This is the primary fat found circulating in our blood. It is an energy molecule, so it can provide energy. We actually store it in a cell type that you'll see in just a second. But if there are too many triglycerides floating in our blood, they can, particularly if their tails are straight, they can clog our arteries and lead to heart disease. This molecule down here is called a phospholipid, and chances are you've seen this before with the cell membrane if you learned about the cell membrane last year in 8th grade. So this is going to help form a boundary. And there are some unique properties about this phospholipid. It is an amphipathic molecule. We have seen that word before. Amphipathic means it has both polar and nonpolar regions. So what's called the head, commonly referred to as the head up here, is polar. So here is kind of in a cartoony drawing. Here's the head of the phospholipid. And then the tails, the 2 tails that stick down, are going to be nonpolar tails. So those are really important polymers, and we see them again when we talk about the cell membrane. Here are the last 2 polymers that we need to know in the lipid world, and these look very, very different. I call these guys the ringed fats. So these always throw students for a loop because students look at structures, they see rings, and they instantly say, oh, that's a carbohydrate. But notice, this is primarily carbon hydrogen. Each one of these corners on these rings are carbons. And then you see carbon and hydrogen groups. This is a big giant hydrocarbon tail. There is one hydroxyl, but it is not loaded down with hydroxyls, which we learned carbohydrates do have that property. So this is actually a fat. It's a ringed fat. And so there's 2 categories of ringed fats that we need to know. This first one is cholesterol. All right, so it is a ringed fat. The rings always look the same. Here's 1, 2 side by side. Then you take a stair step up and you see 2 more. So there are 4 total rings in a cholesterol molecule. There's 4 rings down here as well. So 4 rings in a cholesterol molecule. Cholesterol is found in cell membranes, but only in animal cell membranes. So this would not be something that we find in a plant cell or a fungal cell or a protist cell or protozoan. We find them only in animal cell membranes. They do float around in our blood as well, and so we'll talk about as we get into Unit 2 why they might do that. They are obtained through our diet. And so think about if they are found in animal cell membranes and we eat them through our diet, what kinds of animals or animal products are you consuming? The meats and the other animal products contain this cholesterol, and that's how you get cholesterol into your body. Now, there's two types. There are LDL cholesterol molecules and HDLs. You maybe have heard of good cholesterol and bad cholesterol. Well, here they are. LDLs are bad. The L, the D, and the L stand for low density lipids. And then HDLs are high density lipids. And so there you have the sortings of if you've ever heard of good versus bad cholesterol, there they are. And then our last category down here, all of these are steroids. And so steroids, again, are another ringed fat. It's really the same ring structure of a cholesterol. Cholesterol can be converted into a steroid if we just take this tail off and pop a functional group onto it. And so the base molecule, this first one is cortisol. I'm trying to read them. This one is aldosterone. Here's estradiol, progesterone. So these are hormones that really have a base structure that is the same, and you just alter these side groups up here. And so a tail can be removed, and then you add a functional group, and you can easily convert cholesterol into a steroid. These are hormones. Testosterone, estrogen are probably the two primary hormones that you know of. All right, that wraps up topic 1.4. We're going to talk about these this week. You'll have another lecture video about midway through the week to cover the last section of notes, which is topic 1.5, the last two remaining macromolecules, proteins and nucleic acids. But for now, you are done.